Now moving on to the final part in our error analysis discussion, which is going to be the linear regression. So what's the linear regression? The linear regression is a method which is used to model mathematically the relationship between two quantitative variables, namely the x and the y variables, where x is labeled to be an independent variable and y is labeled to be a dependent variable, meaning that y depends on x. The values of y, they depend on the values of x. They varies with them. For example, if we consider that the values of x are actually increasing while the corresponding values of y are also increasing, therefore, graphically we can represent that relationship with an ascending straight line. So the relationship between x and y is a positive relationship. Moreover, the slope of that straight line is actually a positive slope. Now if we consider that the values of y are still increasing, however the values of x are still increasing, however the values of y are decreasing, therefore we have a negative relationship between x and y, which is represented graphically by a descending straight line which has now a negative slope. Now let's consider that we have multiple observations for x and y, meaning that we have multiple experimental values for x and y that we need to plot in that xy plane. So we are going to consider the following xy plane in which we are going to be plotting the observations for x and y. I'm going to be choosing them in an arbitrary manner. So we have a point here, a point there, another point here, so on and so forth. So let's consider that we have the following values for the xy plane. They are experimental values that were determined in the lab. Now what we need to do next is actually we need to find a straight line that can fit through as many observations as possible, or that can fit through as many data points as possible. In other words, we are going to be locating the maximum amount of observations that are actually situated along the same straight line. So if you look over here, we can see that these 4 points, they are somehow located along the same straight line, so we can join them. So in that case, by joining these points, we are going to be defining none other but the regression line. So that straight line over here, it actually consists of the so-called the regression line. The regression line is actually an estimated line. Why it's an estimated line? Because we are actually estimating it by relying on our observations. So depending on the observations and depending on which data points are actually residing along the same straight line, we can define the so-called regression line. Now if we look over here, we can clearly see that there are other points that have been left out from that regression line. Therefore, any discrepancy, any difference that exists between these data points and that regression line, they consist a margin of error, an amount of uncertainty that we need to determine. So for example, if we extrapolate that point down to the regression line, if we take the perpendicular from that point down to the regression line, that gap over here, it actually consists an amount of uncertainty or an amount of error that we need to determine. So let's say, for example, over here we have the coordinate xi, the coordinates xi and yi for that experimental point. Over here for that estimated point, so that point over here we are going to call it the estimated point, and that point over here is going to be referred to as the experimental point. So the difference that exists between the experimental point and the estimated point, it consists a certain margin of uncertainty. Now why do we call it the estimated point? Because it is actually the location where we expect our experimental value to be located in order for it to be precise. So that estimated point over here, let's say, now it has the same x coordinate as the experimental point xi, however now it has a different y coordinate, which is y. And the same thing for the rest of the points. By extrapolating each point, by taking the perpendicular from each point toward the regression line, we would be actually defining over here the so-called the amount of uncertainty that exists between the experimental points and the estimated points. So over here, let's call this one to be E1. So that point over here is going to be called E2, and over here E3. So E1, E2, and E3, they correspond to the gap or to the amount of uncertainty that exists between the experimental point and the estimated point. Now how can we find that gap in that case? By definition, EI where I it goes from 1 until n number of trials, EI is equal to the difference between the y coordinate of the estimated point and the y coordinate of the experimental point. So EI is equal to the difference between the y coordinate of the estimate point and the y coordinate of the experimental point. In other words, EI is equal to y minus yi, where y over here it corresponds to the y coordinate of the estimated point, and yi it corresponds to the coordinate of the each experimental value which is not residing along that straight line. Now, what would be the equation of y in that case? Noting that y is none other but the y coordinate of each estimated point. Now, these estimated points, they are actually residing along a straight line. And we know that the equation for a straight line is given as y equal to ax. And we can also add to it a y-intercept plus b. So we have y equal to ax plus b. So in that case, a over here is going to correspond to the slope, and b over here is going to correspond to the y-intercept. And altogether, the slope and the y-intercept, they actually consist of the constants of the regression model. So the slope and the y-intercept, altogether they consist the constants of the regression model. So in that case, that equation over here of EI becomes EI equal to y minus yi, where y is equal to axi plus b. So y is equal to axi plus b minus yi, where yi would be, like I said before, the y coordinate of the experimental point, which is not actually residing along that straight line. Now over here, if we look at that equation, EI equal to axi plus b minus yi, we actually have two unknowns that we need to determine. We have the slope and we have the y-intercept. And in a bit we are going actually to discuss how we are going to be determining the slope and the y-intercept. Where xi and yi, they are going to correspond to the x and the y coordinate of each experimental point which is not located along that regression line. So in that case, we start, let's say, by finding E1 which is equal to the slope times x1 plus the y-intercept minus y1. Then we find E2 which is equal to the slope times x2 plus b minus y2. Then we have the third error which is equal to a times x3 plus b minus y3, so on and so forth. Let's say that we have n values for EI, for that error over here. So we have En is equal to, or EI, let's call it EI instead. So we have EI equal to AXI plus B minus YI. So after establishing all of these amount of errors or all of these amount of uncertainties between the experimental value and the expected value, we cannot do anything about them. We cannot find any numerical value without finding a value for the slope and a value for the y-intercept. Now, how can we find a value for the slope and a value for the y-intercept? Or better yet, how can we find an expression for the slope and an expression for the y-intercept which are going to enable us to find values for the slope and the y-intercept? To find an expression for A and an expression for B, we are going to rely on a method which is called the least square fitting method. Before we proceed with that method, you have to keep in mind that whatever method you have learned previously to find the value for the slope, which is delta y over delta x, that method, it cannot be applicable in our case, in our lab. It is actually wrong. Like, if you apply that method, it's going to be considered wrong because you are taking into account only 2 observations or only 2 data points of your entire data set. Therefore, you are not taking into account the entire measurements that you have. Therefore, your answer is not going to be precise. So whatever conventional method you have learned to find the slope, that method cannot be applicable in our lab. We have to rely on the linear regression method, which I'm going to lay it out in a few. So for that matter, we are going to be following a method which is called the least square fitting method. The least square fitting method consists of deriving the equation for the error that we have established over here once with respect to the slope and another time with respect to b. In other words, we have the derivative of the summation of vi squared with respect to slope equal to 0, and then we are going to consider the derivative of the expression of the summation of vi squared with respect to the y-intercept equal to 0. So what is actually the summation of vi squared in that case? Over here we have established several equations for the margin of uncertainties that exist between each experimental value and the estimated value. What we are going to do next is we are going to be squaring each value of the error. So over here we are squaring each equation as well. After squaring these equations, we are going to be adding them up. So at the end over here we have summation of vi squared, where I, it goes from 1 until n number of trials, which is equal to the summation of axi plus b minus yi squared, where I also goes from 1 until n number of trials. So the summation of vi squared is equal to the summation of axi plus b minus yi squared. So over here what we are actually deriving is, we are deriving that equation once with respect to the slope and we equate it to 0. Then we are deriving that same equation with respect to the y-intercept, and then we equate it to 0. So overall we are going to be having over here 2 equations of 2 unknowns that we need to determine. I'm going to leave the derivation up to you. I'm not going to be deriving these equations since they are going to be time consuming and they are not very important in your case. You are not responsible of the calculus behind finding an equation for A and an equation for B. But if you are curious, you can try the derivations at home. Like I said, you are going to be deriving that equation with respect to A, and then that same equation with respect to B. You are going to get 2 equations of 2 unknowns, and then you are going to solve them in order to find an expression for A and another expression for the y-intercept. So after doing the derivations, you are going to find the final forms or the final equations for A and B. For the equation of the slope, it's going to be of the following form. It's going to be equal to the number of trials times the summation of each value of xi multiplied by yi minus summation of all the xi's multiplied by all the yi's divided by delta. So basically that equation is stating that A is equal to n number of trials, or the total number of trials is multiplied by what? It's multiplied by the summation of xi times yi. So it's multiplied by x1 times y1 plus x2 times y2 plus x3 times y3, so on. It depends on how many number of trials do you have. Minus what? Minus the summation of all the x values. So you are actually summing up all the x values that you have. So let's say x1 plus x2 plus x3 multiplied by the summation of all the y values. So into y1 plus y2 plus y3. Divided by what? Divided by delta. Delta doesn't have any significance physically, it doesn't have any meaning, but delta is simply a notation which is used in order to simplify the denominator. And delta in that case is given as n times summation of xi squared minus summation of all the xi's squared. So over here you have to pay attention to that difference between these 2 notations. They are not the same, they are different notations. So delta is actually none other but n times summation of xi squared minus summation of all the xi's squared. So basically over here in that first term, what we are doing is we are squaring each term of xi separately, and then we are summing them up. While over here we are summing up all the xi's, all the individual xi values, and then we are actually squaring the final term that we are getting for the xi's. So like I said before, the denominator is actually replaced by delta, which is simply a notation that is used in order to reduce or to simplify the denominator for you. That would be for the expression of the slope. Now, in a similar manner, b over here now is equal to summation of the xi squared times summation of all the yi's. So the y-intercept now is equal to summation of xi squared, meaning that you are squaring each individual value of xi and then you are summing them up. So it's x1 squared plus x2 squared plus x3 squared into what? Into summation of all the yi values into y1 plus y2 plus y3 minus what? Minus summation of all the xi's, so you are summing up all the xi values minus x1 plus x2 plus x3 into what? Into summation of xi times yi. So it's similar to that term over here. So actually you have x1 times y1 plus x2 times y2 plus x3 times y3, so on and so forth. So into x1 y1 plus x2 y2 plus x3 y3, so on and so forth, divided by delta. So that would be for the expressions of a and b. However, we can clearly see over here that if we want to find a and b manually, meaning that if we want to be actually finding, if you want actually to be multiplying each xi by yi and then finding the total summation, and if you want to do the same thing over here and the same thing for the denominator, if you want to find them manually, finding a value for a and b alone is going to be very time consuming, and it's going to take up to half an hour in order to finish the calculations for both. So in that case, we are going actually to resort to a numerical method, to a method which can be applicable on the calculator, which is going to enable you to apply the linear regression method on the calculator in order to find immediately a value for the slope and a value for the y-intercept. So instead of going through all of these manual ways in order to find the value for b and the value for a, which is going to be not only very time consuming, but it's going to be also prone to error in calculations. So there's a high chance that you are going to be committing an error whenever you are doing your calculations for a and for b. That's why we are going to revert to another method that can be applicable on the calculator, where you can be applying the linear regression method in order to find the value for a and the value for b. So over here I have written down the steps that you need to follow in order to find the value for a and the value for b on the calculator. And these steps are actually specific for the FX 991 calculator. So if you have a different model, try to find the specific steps for your calculator, and if you weren't able to, send me an email and let me know. Now for the method on the calculator, first off you are going to click on mode. Then after clicking on mode you are going to click on stat. After you click on stat, a bunch of equations are going to appear in front of you. You are going to choose the equation which corresponds to a straight line, which is none other but a plus bx. However, here you have to keep in mind that b is actually multiplied by x and not a. Therefore, b in that case is going to correspond to the value of slope on the calculator, while a is going to correspond to the value of the y-intercept. So previously we have defined that equation to be ax plus b, where a was the slope and b was the y-intercept. But on the calculator it is actually flipped. b is multiplied by x, therefore b would be the slope and a would be the y-intercept. After you choose a plus bx, two columns are going to appear in front of you, a column for x and a column for y. In the column for x you are going to enter all the x values, while in the y column you are going to enter all the y values. But here you have to keep in mind that if your units aren't in SI units, therefore you have to convert them before you insert them in here. Meaning that if x was in centimeter and y was in millinewton, therefore x has to be converted to meters, and therefore you are going to be multiplying each value by 10 to the negative 2. And the same thing for the y values, you are going to convert them to newtons, for example, meaning that you are going to multiply them by 10 to the negative 3. After you enter the values for x and y, you are going to click on AC. After you click on AC, you are going to click on Shift, followed by the number 1. After you do so, a bunch of modes are going to appear in front of you, you are going to be choosing the REG mode. The REG mode, which actually stands for regression. After you choose regression, now a bunch of symbols are going to appear in front of you, A, B, and R. Like I said before, on the calculator, A is going to correspond to the value of the y-intercept. So by clicking the number that corresponds to A, therefore you are finding the value for the y-intercept. However, in order to avoid confusion between the notations in here and how we have defined them previously, you should write down that the y-intercept is actually equal to B, which is equal to the value of A on the calculator. And then you have the second symbol, which is B on the calculator. B on the calculator, it corresponds to the slope. So by clicking the number that corresponds to B, you will be finding the value of slope. Therefore, over here, write down that slope is equal to A, which is equal to value of B on the calculator. And finally, we have R. What is R? We haven't introduced R before. R is actually a correlation coefficient, meaning it correlates the values of X to the values of Y in order to find if we have a strong linear relationship between X and Y. So in that case, if R is closer to 0.99 or closer to minus 0.99, that implies that we have a strong linear relationship between X and I. So R is simply, it's an indication of how strong the linear relationship between X and Y is. So when you click on R, if you have a value which is close to +1 or to -1, therefore that implies that we have a strong linear relationship between X and Y, meaning that we are actually validating the presence of the linear relationship between X and Y. So we are validating the presence of the linear relationship between X and Y. So that would be for the steps on the calculator, the steps that you need to follow in order to find value for A value for B, and a value for R. Moreover, delta, which we have defined it previously, now we are going to need it later on, and you are going to see where. That expression of delta over here, it can also be found on the calculator, or the value for delta, it can be found on the calculator. However, the method for it, it requires few steps, it requires few clicks. It's not very straightforward, meaning you don't have a symbol for delta alone on the calculator, but rather you have to be finding each individual symbol separately. So, in that case, after you click on shift followed by the number 1, instead of choosing regression, you are going to be choosing sum. After you choose sum, a bunch of symbols are going to appear. You have a symbol for summation of xi, symbol for summation of yi, etc. And over here you have a symbol for summation of xi squared, etc. So you are going to be applying that same equation over here on the calculator, meaning that first off you are going to click on that symbol, summation of xi squared. After you click on it, you are going to click on the product sign on the calculator, times what? Times the number of trials. So let's say you have 3 trials, times 3. Then you add a minus sign on your calculator. So you click on the minus sign in order to add it. Then again you click on shift 1. After you click on shift 1, you choose sum. But now you are going to be choosing the summation of the x values. So over here, minus summation of the x values, and then you are going to square it yourself. You are going to add a square to it, and therefore you have applied that equation of delta on the calculator in order to find a value for that symbol. And like I said before, you cannot find it in a straightforward manner, but rather it requires a few clicks in order to get to it. And later on we are going to see why we are going to need to find a value for delta. So now after finding A, B, and R, we can go back to these values that we have found, or to these expressions that we have found over here, which corresponds to the amount of uncertainty that exists between the experimental value and the estimated value. So you start over here by plugging the value of A and the value of B. You already have values for x1 and y1. You start by finding E1, and the same thing over here. You plug in the value for A and the value for B. You already have the values for x2 and y2. You find E2, and the same thing for E3. Now after finding the slope, after finding the y-intercept, After finding all the EI values, now what's left is to find the error on slope. How can you find the error on slope? So far in the regression model, we have defined the slope, and we have defined the method which is used to find an expression for slope or to find a value for slope. We have also determined the y-intercept, and we have also found, we have also established a way how to find the value for the y-intercept on the calculator, and we said that both a and b, they correspond to the constants of the regression model. Then after doing so, we had actually to find the margin of uncertainty that exists between each data point that we have and the estimated point. So we started by finding E1, E2, E3, E4, etc. And we said that E1 would be equal to AX1 plus B minus Y1, E2 would be AX2 plus B minus Y2, E3 would be AX3 plus B minus Y3, and E4 AX4 plus B minus Y4. Now what's left is to find the uncertainty on the slope. So we need to be finding the uncertainty on slope. So after finding all of these values over here, and after finding also an expression for delta, now the expression of slope is going to be very simple to apply, or the expression for the error on slope is going to be simple to apply. The expression of the error on slope is given as sigma a squared. It's denoted as sigma, but it's not a standard deviation. It's an error. It's an amount of uncertainty. Sigma a squared equal to n over n minus 2 times summation of ei squared over delta. That implies that sigma a is equal to square root of that equation. So in that case, the uncertainty on slope is given mathematically as n over n minus 2, so number of trials divided by number of trials minus 2, times summation of ei squared divided by delta. So over here we have found each ei separately. So now what we need to do next is we need to be squaring each value of ei. So we square the first one, the second one, the third one, and the fourth one. After squaring them, we are going to be summing them up. So we sum all the ei's and you find their values, and then you plug it in that equation. And delta, I have already shown you how to find it on the calculator, and you already have the number of trials. You plug these values in that equation, and therefore you'd obtain a value for the uncertainty on the slope. And like I have mentioned before, whenever you are finding an uncertainty, whenever you are finding an error, the error has to be reported with only one significant figure, with the exception if the leading digit in your error is actually 1 or 2. Therefore you have to report the answer for the error with a maximum of 2 significant figures, meaning you have to retain 1 digit after 1 and 1 digit after the number 2. So now, after introducing the concept behind the regression line, the concept behind the regression model, whether in terms of slope, in terms of the y-intercept, in terms of the uncertainties that exist between the experimental values and the estimated values, and after defining the expression which we have used in order to find the error on slope, now we are going to try to apply these methods on an example which is related to a physics problem. The sample problem that we are going to solve is going to be similar to the one that we have solved during the standard deviation session. So we are going to consider that we have a solenoid and we are varying the current that is being applied to that solenoid, and each time we are determining the corresponding magnetic field that is being generated by that solenoid. However, in the case of the standard deviation, we had here a third unknown, which was actually the number of turns. But in that case, in the case of the linear regression, we don't have a third unknown, but rather we are studying the relationship between an x and y variable. In other words, between the magnetic field and the electrical current. Now, the first question in such type of problems is going to be common, is going to be always similar. They are going to ask you to write down the relationship which relates x to y, or which relates these two variables over here, these two parameters. So you are going to write down the relationship relating the magnetic field to the electrical current. So B is equal to mu 0 times N times the electrical current over the length, where N would be the number of turns of the solenoid, L its length, and mu 0 would be the magnetic constant. Now the second question is going to be to use linear regression. So over here they are asking you that they are actually telling you that we are dealing with a linear regression problem. So you don't have to guess if you have a standard deviation problem or if you have an error of propagation problem, but they are specifying for you that you are dealing with a linear regression problem. They are asking you to use linear regression in order to determine the slope of B versus I along with the y-intercept. So over here they want you to find the slope of B versus I. So by specifying the slope of what versus what, therefore they are specifying for you which parameter is going to be x and which other parameter is going to be y. So over here B is going to be the y variable and I is going to be the x variable. So keep in mind that whenever you have the slope of something versus something else, that first something over here, that first parameter is going to be the y variable versus that second parameter is going to be the x variable. It's always the slope of y versus x. So to find the slope, we are not going to revert to the manual method, meaning that we are not going to be applying that long equation that we have established before, but rather we are going to apply the method on the calculator. And also here keep in mind that you cannot apply whatever conventional method that you know for the slope from high school, meaning you cannot find it by applying delta y over delta x, since like I said before, that method only relies on a couple of values from your data set, but it does not rely on the entire data set. So that's why we are going to revert to the steps that we have actually established on the calculator. So over here, after you click on a plus bx, two columns for x and y are going to appear in front of you. In the column of x, you are going to enter the values for the electrical current. So over here you enter I1, which is 1, I2, which is 1.8, I3, so on and so forth. And in the y column, you are going to be entering the values for the magnetic field, which are B1 equal to 5, B2 equal to 8, B3 equal to 10, and B4 equal to 12. And after you enter these values, you click on AC followed by Shift 1, you choose regression, then you have the values for A, which is the y-intercept, and the value for B, which is the slope. And therefore you have covered the number 2 part. Now moving on to question number 3. In question number 3, they are asking you to determine the error on slope. We have seen previously that for the error on slope, the equation is given as sigma A equal to n over n minus 2 times summation of I squared divided by delta. So over here we still have some unknowns that we need to determine, which are what? Which are the margin of error that exists between each couple of x, y and the estimated values, meaning that you have to find EI, which is equal to y minus yi, for each couple of values that you have over here. So in that case, we are going to be adding a new column to that table. So in the table, we are going to assign y to be equal to the y variable and the current to be equal to the x variable. And then we are going to be adding a new column for the EIs. So over here we have EI, which is equal to AXI plus B minus YI. And then you start by finding each term of EIs. So you start by finding E1, which is equal to the slope times x1. x1, which is none other but 1 over here, which is the first value of the electrical current, plus the value of the y-intercept minus y1, which is the first value of the magnetic field, which is 5. Then you have E2, which is equal to A times 1.8 plus B minus 8. Then E3, which is equal to A times 2.7 plus B minus 10, so on and so forth for the last trial. Now after you find all the EIs, as we can see in the equation of the error, we have the summation of EI squared, meaning that we need to be squaring each term of EI and then sum them up. So we are going to be adding here now an additional column for the EI squared. So you start by squaring each term of EI, E1 squared, E2 squared, E3 squared, and E4 squared, and finally you sum them up. So we have found the summation of EI squared, we already have the number of trials, we are still left to find a value for delta. So like I said, to find delta, you can actually apply a method on the calculator, which is not going to be a straightforward method. It requires few clicks, but it can give you a value, an accurate value for delta instead of doing it manually. and therefore subjecting your answer to any error in calculations. So on the calculator, after you enter the I values and the B values, and after you click on Shift 1, instead of choosing regression, you are going to be choosing sum, and these symbols are going to appear in front of you. You are going to be applying the equation of delta on the calculator in order to find value for it. So on the calculator, you choose the summation of xi squared, you multiply it by the number of trials, then you add a minus sign, then you have to choose over here the summation of xi, and you are going to be squaring it yourself, and therefore you have a value for delta. So having a value for delta for the summations and for the number of trials, therefore you can find an answer for the error on slope. And as I have mentioned before, whenever you find the error on slope, you have to choose the right number of the significant figures, and you have to include the unit of the slope, which is going to be the unit for the error on slope, which is going to be the same unit as the slope itself. Now in question number 4, they are asking you to identify the expression which represents the slope. How can we identify it? So we have that equation over here, b equal to mu0 and I over the length. And we know that b represents the y variable and I represents the x variable. We know that the equation of a straight line is y equal to ax. So the slope is always multiplied by x. So over here, after identifying the x variable, you check which terms are actually multiplied by I, and that would be the expression of slope. So over here we can see that mu0 n over L is actually the term which is being multiplied by L. Therefore the expression of slope would be equal to mu0 n over the length. That would be the expression of slope. Now in question number 5, they ask you to deduce from the slope the number of turns of the solenoid. Now in part number 2, we have actually found a numerical value for the slope. And in part number 4, we have found the expression for slope. So by equating the numerical value to the expression of slope, which is mu0 n over L, you can find that the number of turns of the solenoid is equal to the slope times the length over mu0, and therefore you get a value for the number of turns. So like I said before, over here you have established an expression for slope, over here you have a numerical value for slope, you equate them and you find the number of turns for that solenoid. Now in question number 6, they are asking you to determine the error on the number of turns. Now how can we determine the error in that case? Which method are we going to apply? Is it standard deviation, is it linear regression, or is it propagation of error? Now of course it's not going to be the standard deviation, since you don't have a set of measurements that all belong to one quantity that you want to find their average and the error on the average. And it's not going to be linear regression in that case, since you are not determining in that part the slope of anything. You are not finding the slope of a certain variable versus another variable, but rather over here you have what? Over here you have the number of turns, which is being expressed in terms of the slope times the length over the magnetic constant. And we already found an error on slope in part number 3. So the slope is no longer a constant, but rather it's a variable. And let's say you have also an error on the length, which was given previously. Let's say that the length, it was given to have a certain error on it, plus minus a certain error on it. Therefore, the number of turns over here is actually a function of two variables, a function of slope and a function of length. Therefore, to find the error on the number of turns, you have to apply the error of propagation method. You have to derive the number of turns twice, once with respect to slope and another time with respect to the length. So the error in that case on n is going to be equal to the derivative of n with respect to slope times the error on slope squared plus the derivative of the number of turns with respect to the length times the error on the length squared. And then you start deriving the first derivative. Like I said, whenever you are deriving with respect to slope, therefore the length will be held a constant. In that case, you are left with the length over mu0 times the error on slope squared, plus derivative, the partial derivative of n with respect to the length. So slope times L over mu0 derived with respect to the length, it would leave you with slope over mu0 times the error on the length. And that would be it. So having the values for all of these physical quantities, you can plug them in, and finally you can find a value for the error on the number of turns. Now let's have another example in order to showcase for you how sometimes the choice of x and y, it can be a bit tricky. It is not very straightforward at all times, like in the case that we have seen before. So let's consider that you have values for the linear density and for the fundamental frequency. So the linear density is actually in kilograms per meter, and the fundamental frequency is in hertz. So let's say over here that you have two borders, and these two borders are connected by a wire, and over here to that wire also you have a certain mass attached. So we are hanging a certain mass from that wire in order to apply a certain tension to it. And each time you are changing the fundamental frequency that is being applied to that tension, and you are determining the corresponding linear density. So you have over here values for mu, which are, let's say, 0.4, 0.6, 0.8, and 1.1. And over here you have fundamental frequency, let's say, of 30 hertz, 45, 60, and let's say 75. They are arbitrary numbers. Now the first question would be, of course, to establish a relationship between mu and f. So the relationship relating the fundamental frequency to the linear density would be f equal to 1 over 2L square root of T over mu, where T would be none other but the tension, which is equal to mg. Mg, which is the weight of that hanging mass. So that hanging mass is actually exerting a tension on that thread, on that wire. Question number 2, they are asking you to use linear regression in order to find the slope of, let's say, mu versus 1 over f squared. So they want you to find the slope of mu versus 1 over f squared along with the y-intercept. So if you look over here we already have a value for mu. We have values for mu. However, we don't have values for 1 over f squared. 1 over f squared is not actually featured in that table. And I have told you before that in order to identify which parameter is y, which parameter is x, you have to look over here at the given slope, or at the given, which is actually indicating for you the slope of which parameter versus which other parameter you want to find. So over here, since we have mu versus 1 over f squared, that implies that mu is the y variable and f squared is actually the x variable. So over here we can assign y to be equal to mu. However, we cannot assign x to be equal to f, since x is actually equal to 1 over f squared. Therefore, in that case over here you have to add a new column for the x variable, which is equal to 1 over f squared. So in that case you are going to be squaring each term of f over here, and then you are going to be taking its inverse. So you are going to be finding 1 over 30 squared, 1 over 45 squared, 1 over 60 squared, and 1 over 75 squared. And these would be the values for the x variable. So now we have identified the x and the y variable. In that case, you can apply the linear regression method on the calculator in order to find the slope of mu versus 1 over f squared. So as we have seen over here, the choice for x and y, it wasn't very easy, since the x variables, they weren't actually featured in that table. And you cannot choose immediately y to be mu and x to be f, or y to be f and x to be mu. You have to go back to the given equation and check the slope of what versus what you are actually finding, and check if these variables are actually given in the table or not. If they are not given, you have to compute them yourselves, as we have done over here. Now after finding the slope and the y-intercept, let's say you want to find the error. So by applying the equation for the error on slope, n over n minus 2 times summation of I squared over delta, you are going to start by finding the EI. So over here you add another column for the EI, which is equal to AXI plus B minus YI, and you start finding each term of EIs. You start by finding E1, which is equal to slope times x1 plus the y-intercept minus y1. Then E2 equal to slope times x2 plus the y-intercept minus y2, so on and so forth. After finding each EI, now you add a new column to find the I squared. you are going to square each term of EI, and finally you are going to sum them up, and then you find delta on the calculator, and finally you have an expression for the error on a slope. Now in question number 4, let's say they ask you to identify the expression that represents the slope. So how can you find it in that case? So we have f equal 1 over 2L times square root of t over mu. Noting that y is actually mu and x is actually 1 over f squared. So we have, first of all, we have to square that entire equation to become f squared equal 1 over full s squared times t over mu. After squaring that equation, now we are going to adjust it in the form to be equal to be of the form mu equal to something multiplied by the x variable, by 1 over f squared. So mu is equal to 1 over 4l squared times t times 1 over f squared, where mu in that case would be y, 1 over f squared would be x, and therefore whatever term that you have over here which is multiplied by x, that would be the expression of slope. So over here we have adjusted our equation to become of the form y equal to a times x, where y would be mu and x would be 1 over f squared. Now after doing so in part number 5, let's say they want you to find the length. So you already have a value for slope, and you already have an expression for slope which is t over 4l squared. You want to find the length, therefore you use the numerical value that you have found for the slope, you plug it in, you plug in the value for the tension, and then you can find a value for the length over here. And finally in part number 6, they ask you, let's say now, to find the error on the length. How can you find the error on the length? To find the error on the length, also we are going now to be applying the propagation of error method. So we have the length equal to the tension mg over 4 times slope and square root for that entire equation, which is equal to half times square root of mg over slope. Now on the slope you already have an error which was found previously, so it's already a variable. And let's say you also have an error on the mass which is also given. So now we have length being a function of two variables, function of the mass and the function of slope. So to find the error on the length, we have to derive it twice. Once with respect to m times the error on m squared, plus a second time with respect, over here we have the main function. Always in the numerator you have the main function. So derivative of L with respect to slope times the error on slope squared. And that would be it. And then you carry on with the derivations in order to establish an equation for the error on L, and then you plug in the values in order to find a numerical value for it. And that would be it for the linear regression analysis and for the error analysis in general.